Okay guys, sorry for the format of this video. It's not quite what I would have liked, but I've just had a nightmare trying to get the software to work properly. So we're going to deal with arithmetic sequences and series, where a sequence is a series of a list of numbers that are separated by commas. So these continue forever. They go 7, 11, 15, 19, 23, and can continue forever. What you should have seen in the past is a basic way of finding them, which is look for the differences, check that each one follows the same difference. If it doesn't, then it won't be an arithmetic sequence. It must always be going up by the same amount or down by the same amount. So we then turn around and we look at it and go, okay, so this is going up in fours. So we know it's something like the 4 times table. What do I need to do to the 4 times table to get the 7? Well, I add 3 to it. Some of you may have been taught to find the 0th term, the term before. That is also the same thing, because 0 times 4 in the 4 times table, it's going to get that to 0 and then add 3. This is the right value still anyway to correct. So that's what you're used to doing. What we're going to do with it is we need to reformulate this slightly. Arithmetic it should be, sorry. So the arithmetic sequence, we're going to reform it. What happens quite a lot of the time is there's different formulations people use. Our exam board uses UN, but you may see people also talking about arithmetic AN sequence as they go through. So what we do with this is we are actually basing our calculations all upon this first term. So rather than counting up the 0th term or the times table and convert it, we're starting with our first term, and then we're saying, right, to get to a position, I need to add 4, but how many times? And the thing to notice is that we add 4 once to get to term 2. To get to term 3, we've got to add 4 twice. So we're always going for the term number less 1. So that's what this formula actually comes out to saying, is that to get to this term, I start at the beginning, I add the difference, and I only make one, I make one less step than the position I want to get to, because we're already in position 1. That gets formulated to a single equation, the UN equals A plus D n minus 1. This value is also, when we come into the next bit, actually we'll talk about the next part. So it's just a reforming of our equation. Rather than having the 0th term plus dn, we're now actually saying the first term and 1 less step. So a series is actually what happens when you want to add together a sequence. Common things happen all the time. It's a common thing we would like to do. So we've got this thing called a series, and the difference with a series is you're adding each term to give you one number. And that value, for it not to disappear to infinity, this number must end, must continue and stop for an arithmetic sequence. So we've got a first term and a last term. Now, even though this is odd, we can do the following tricks. So this is based upon a technique that's been attributed to a guy called Carl Friedrich Gauss, who as a very young lad was set the problem by a very lazy tutor who said, go on, work out all the integers from 1 to 100. And I'll take a snooze for half an hour, thinking it would take him ages. Within 5 minutes, Gauss had come back with the answer. Now, he says that he added them all up, but what's suspected is this is the sort of trick he did because he was shown to use it again later. What is it I want to do? Well, I want the sum, capital S, of the first 100 integers. 1, 2, 3, 4, 5, 6, keep going until 99, 100. Well, that's the same thing if I flip it round. Sum to 100 of all our digits. So we're going from 100 down to 1 now, 100, 99, 98 to 1. Well, if I do that, each position gives me 1 plus 100 is 101. 2 plus 99, 101. 3 plus 98 is 101. So if I pair these off, I wind up getting the same number repeated, and I get 100 pairings. So the sum of these two sequences is going to be the number of terms times the first and the last sequence. First term, last term. Second term, second to last. Same total as the first and last. So sum of the 100 is going to be my number of terms times that sum of first and last divided by 2. And he correctly said the value was going to work out as 5,050. So to summarize that, the formula comes from the number of terms multiplied by the first and last term. You've got to be able to work that out and divide it all by 2. So let's bring this back over to the left-hand side. That's this first form of the equation. But this last term is also given by this formula, a plus d n minus 1. So if we substitute it in, we're going to get n over 2, 2a plus dn minus 1. 2 standard formulae, just done by flipping down the sequences, pair them off, and if we do that to this one, we actually try doing this flip and write out, what we get is 7, 23, 11 and 19, 15 on its own, but it's going to match with a 15 coming down. We've got 19 and 11 and 23 and 7. They all work out as 30s. So first and last, 30. 30 times 5, 150, divided by 2 gives me the 75. If you add those together, you get 75. Try this formula. Well, our first term was 7. Our differences are 4. And the number of terms I want is 5. Put it into the formula, 5 over 2. And I would write it out this way for the examiner. Make sure they see that you are putting each value in, not do parts of the calculation. Show them you put the values in, because quoting the formula probably won't get you the mark, but substitution correctly is more likely to give you a mark. So 2 times 7 plus 4 times the number of terms minus 1 gives me 5 over 2 times 14 plus 16, 30, and I get my 75 back. Another way of doing it. So this works out each time. Or do the first plus last, 30, times number of terms, 5, 150 divided by 2. Yeah, that's my 75. 3 different ways. So let's try doing the sum of the first 10 odd numbers. So for the first terms of odd numbers, you may remember from proofs, there is a standard formula for odd numbers. Even numbers is going to be 2n. Odd numbers will be 2n minus 1 if you're beginning at 1. So we're going to try and write the sum of those numbers. So this is my odd number. Has an a of 1 and a d of 2. Now they may show you it with sigma notation. Now sigma notation is summation. We've done it in statistics. So this says start with the first item, go to the 10th, 10 items. You apply this formula, the UN formula. So that's what this is. If you read this formula, that's your difference. And if you put 1 in, it will tell you what the first term is, but you've got to put 1 in to give you that number. Okay. I'll add that on as a little note here. So going from there to there, n equals 1 gives you a for our formula. So if I want to do the first 10 odd numbers, what we need is n divided by 2, 2 times the first term, plus 2 times the number of terms minus 1. Gives me 100. If you actually write the first 10 odd numbers down, add them up, you get 100. If you do the first and last pairings, 20, 20, 20, 5 pairs of 20, 100. Still works. Doesn't have to be simple, straightforward sequences. If I'm doing a sum based upon this formula, I've got to identify the key parts. So the first term, n is 1. Make sure n is 1 goes in. You've got to do that to find the first term. Don't just assume minus 2. That is a caution. Make sure you do that calculation. Okay, don't ignore it. The difference is the part in front of the n term. So we want to do 10 terms, put it in, n over 2, 2 lots of a, plus a half of n minus 1. N minus 1 is 9, half of that is 4.5, 2 lots of minus 5 is 3, times by 5 gives me 7.5. Now what's interesting with this one is there is a number pattern one which happens quite nicely with this. And that's if you write them out, you'll notice the first 7 terms are symmetrical, about 0. 0 is in the middle, and then each of these numbers pair off to give us a total of 0. Worth remembering as a trick. So that's my first 7 terms. 8th, 9th and 10th are the ones which are giving my total. So what I did was I started with the first term, minus 1.5, followed the pattern, adding 0.5 each time. Keep going until I get to the 10th term, then balance them out. Okay. One last example. Back to the odd numbers. What are we going to do? And there are 2 techniques to this. One I would caution you against, but I will show it. Odd numbers. So I want the sum of the 4th to the 10th odd number. So we're using the same formulae that we were using a bit before. It's still 2n minus 1. So I want the sum of the 4th to the 10th term of 2n minus 1. How can I calculate that using my sums? Well, I want to add these numbers up. The 7, 9, 10, all the way to 19. Well, I can do the sum to 10 using my formula. So that's 1, 3, 5, 7, 9. But the ones I don't want are the first 3. I can take that sum away and I'm left with the sum of these. So just be careful. We need 1 less when we're doing the sum for this bottom part, the takeoff. So to do the first 10, well, first of all, first term is 1, difference is 2. The sum to 10, as we saw before, is 100. The sum to 3, 3 over 2, is 2 lots of a, 1, plus d, 2, times 3 minus 1, the position, or number of steps. Work that through and you get a sum, 9. So the sum of these is the difference between these 2 numbers. Sum 10 minus sum of 3 gives me 91. If you actually add these up, yes, they do go to 91. If you're comfortable with that and don't want to push yourself any further, or want to come back to this next bit later, there is an alternative, but there's a couple of risks with it, in that we will redefine our sequence. So stop. If you don't need to, if you're happy with what you've just done, that was fine. Go and get some practice. The extension part to this, if I can just, I'm going to insert a space here so I can separate the final slides out. So the alternative way of doing this is redefine our sequence in terms of these numbers. So my first term is now 7. My difference is still 2. And my number of terms now needs to do, instead of doing the one less in this subtraction here, we're doing one less of the numbers of terms that we're doing. So we do need term 10, subtract off up to term 3. So we're doing the 4th to 10th terms. So 10 minus 3 is 7. Put that into this formula, we're using these, and we again get 7 times 13, which is 91. We get the correct expressions. So to finish up, let's do a quick summary of the formulae. So our summary is we've redefined our series, our sequence. Our sequence terms now we do in terms of the first term plus the difference and do the number of steps needed to get from the first to the whichever term is needed. When we go into series, trying to get the sums of these, there are two forms of the equation. You can do the number of terms divided by 2 multiplied by the first plus the last. That should be familiar to you. It's pretty much a trapezium area calculation. Okay? Or substituting for L with the last term, and that will give us n over 2, 2 lots of the first term plus the difference times n minus 1. The n minus 1 is the important steps in this today. And if we want to do a sum, not starting at the first term, we want to do it from a sum from the 5th to the 12th. Remember, we've got to do from where we want to sum up to and take away up to the value, not the first value in my sequence. So that needs to be taken out. Some people will do sk minus si and then add on u in position I, because that will give you that position, or plus a. That will also work, but it's a funny little side thing. So you could also do the sum of k minus the sum of I, but then add on u at I, which is basically adding it on the first term. Okay, hopefully this time it's recorded. Oh, don't.